Hello again, abstract algebra students, and this is Danny Klein. This is your third Chapter 0 video and the last one on this first section. As I've sort of split them up, you can see in the schedule how I've split them up. So this one is on the last theorem in that first section, which starts with the well-ordering principle, and also on the Euclidean algorithm, which isn't quite presented as a theorem, although you can prove it like a theorem anyway. It's just phrased a little bit differently, but that's what we're going to be taking on today. One thing I do want to mention here is proof of the Euclidean algorithm is fairly rarely given in textbooks. I'll verbally sort of describe how it's proved, but I'm not going to go over the entire proof for that. The first theorem that we have up there, the theorem that the book says Gcd is a linear combination of A and B, that is actually a theorem that is proved in the book. I'm not going to prove that one out for you. It's another proof that involves the use of the well-ordering principle, so it has all the same issues of the proof of the division algorithm, which I talked about in the first video. So, like I said, proofs involving the well-ordering principle itself are fairly rare, and you don't use them. You don't use it to prove many things, and when you do, it's early on, and then you use those results to prove other things rather than using the well-ordering principle again. That's just the way it generally goes. Okay, so let's get into these two theorems. First of all, the text thing here, let me actually edit this a little bit. The text thing wants me to capitalize GCD for some reason, so I'll just go ahead and capitalize it everywhere. There we go. There we go. That way I don't have to worry about it later. The book doesn't capitalize it, and I don't usually capitalize it, but, computers are what they are, and they tell you what to do, and you have to obey, because our mechanical overlords will not be satisfied otherwise. All right, so here we go. Let's actually take a look at this first theorem. If we have any integers a and b, not both 0. So in other words, integers for which you could say the GCD is defined, right? Essentially, you want something, you want the largest common divisor of both numbers. So if they're both 0, we don't have a way to define that, but if at least one of them is non-zero, we can define it. And usually you don't worry about it in the case where one is 0 anyway, but you can define it there. Then there exist integers x and y such that x times a plus y times b gives you the GCD. Now you'll notice this is, let me zoom in here a little bit. Hang on, let's do it this way. This is a there exist. There exist integers x and y. That's not saying that x times a plus y times b for any x and y are going to give you the GCD. That means there are specific x and y here that do that. So specific x and y make this statement true. Now, one thing you might not notice initially about this that is usually addressed in these kind of proofs where you're claiming the existence of a certain thing is that these integers x and y in this are not claimed to be unique. If a result says that something exists and it's unique, then there should be only one instance of it. Here, they're not saying that it's unique. So at first you might say, well, we might not know whether it's unique or not. As it turns out, it's easy to show that they're not unique. In fact, I'd like for y'all to pause the video and think about this. This is, I know, a general case, so we're just using letters here. But think about how you might pick, once you know one pair of integers, x and y, how you might pick another pair that also makes that work out, make that equation work out. So pause the video and then come back when you're ready. Okay, so let's talk about how this would work. I'll do it sort of on below here. Let's put this in, what, red. Okay, so if I've got, let's see here, if ax plus by equals the GCD, I can make new numbers here. And there are lots of ways you can do this, but I'm just going to show you one example. We could say then also we're going to have a times x minus b plus b times y plus a. And this might be the example that you all came up with if you came up with one. What you'll wind up finding here is this gives us, what? Let's zoom in again. Ax, if I remember how this worked, minus ab, then plus by plus, I gotta zoom. Okay, plus AB, and you'll notice that by subtracting b from x and adding a to y, I get AB twice, and I am able to cancel those two things out, right? They go away. And then what I'm left with is just ax plus by, which we already saw was the GCD. So this already shows us that these numbers aren't unique. We've got a second case once we have a first case. It's also pretty easy to make other cases. And in fact, later on in the, well, actually we don't do this in this class. In the number theory class, if you're taking that in the spring, which I think it's this spring, we actually come up with a complete list of, once we have one example, how to come up with all the examples that satisfy this. But one thing you might do is you might think about this b that you've got here and this a. You could just multiply them by the same constant. So minus 2b plus 2a, that would work as well. And once it works for 2, it'll work for 3 and 4 and so on. So you don't, there's not just one way to get a new one from the old ones. I should probably actually cross those out instead of just using, in fact, let's, oops. Okay, let's cross these out rather than using the highlighter. Okay, so that is how this theorem works. It's not unique. Now you'll notice that this theorem, even if you go through the proof in the book, it doesn't really give you a good method for finding these values x and y. Now you might say, would we ever need them? And the answer is yes, sometimes we do need them. And the next thing we're going to go over, this Euclidean algorithm, even though its main purpose isn't to find those integers x and y, we can use it to find those integers as well as what its main purpose is for. Okay, so let's go ahead and look at the Euclidean algorithm, and we'll figure out how that works. Again, like I said, I'm going to sort of verbally describe how the proof of this works. It's fairly straightforward to follow, but it does have some indeterminate number of steps. It's a finite number of steps, but you don't know what it is. It's based on the integers you start with. So it's you do have to figure that into the proof, but we'll just talk about it rather than actually write out a proof in words here. Okay. So the Euclidean algorithm. Let's use this, maybe in red. For integers, A0 and B0. Now, the book has these as subscripts. Unfortunately, this PDF editor, the typing doesn't make making subscripts easy for me, so I haven't figured out how to do it yet, so and there might not be a way. So I'm just using A0 and B0 here to represent A sub 0 and B sub 0. They're each one number. I'll do them with subscripts later on, but when I'm writing it by hand, but this is the easiest way to do it, typing. So we can use the following algorithm to find the GCD of the two numbers. So we start with two numbers, we want their GCD, we use this algorithm. And the nice thing about this algorithm is it's just a bunch of repeated uses of the division algorithm. And the division algorithm is something that technically we just learned, but remember, it works just like long division. So you've known this since the 4th grade or something. So it's a little bit rearranged, but it's essentially just dividing A by B is what we're going to be doing. So first, we are going to use the division algorithm, and we're going to write A as, nope, this one here, A as a multiple of B plus a remainder. And the remainder here is between 0 and B. That's our first step. Now, one thing I do want to mention here, A0 traditionally is the bigger of the two numbers. So you have A0 and B0. Traditionally, you use A0 as the bigger, B0 as the smaller. It doesn't have to be that, but it does wind up working that way eventually anyway. So usually it's the steps better follow one another if you start off with A0 as the bigger number. So what we've got here is something we know we can do. We've done this with the division algorithm or long division since we were little kids, but we can use the division algorithm here to write A equals B0 times some quotient plus some remainder. Okay, so at this point, that doesn't give us the GCD. If it did, finding GCDs would be easier than it is. But what we've got to do then, oops, don't want that, is we have to repeat the division algorithm. So here, what we want to do next is we want to take A1 equal to B0 and B1 equal to R0 and repeat the division algorithm. In other words, we're going to have A1 equals Q1 times B1 plus R1. Now, in this sense, it looks just like what we did before, except the subscripts all jumped up by 1. But it's important to know that some of these numbers that we have here are actually numbers from the previous step. And if we write them in those terms, we get something that looks like this. B0, so that comes down from above. R0 also comes down from above, and we get this new division algorithm. So our smaller of our two original numbers divided by our original remainder, and we get a new remainder smaller than the original remainder. And that's important here. This new remainder, let me zoom in here. This new remainder that I've got right here, let's try and make that a better circle. Right here, this new remainder is smaller than our original remainder. And not just smaller than or equal to, smaller than. And what that means is the remainders in this are a strictly decreasing sequence of positive numbers. So that means your remainder in one step has to be smaller than your remainder in the previous step. And what you do with that knowledge is you just repeat the process. Eventually, your remainder is going to get to 0. Once you have that remainder as 0, the last non-zero remainder is the GCD. So here, the way I've written this, the r sub n equals 0. That means r sub n minus 1 would have been the GCD. And the way this works, each one of these remainders has to be a divisor of both of the numbers that you started with, just because of the way it works out, and that's why you get that as your GCD. So let's actually do an example of this. And I didn't mention this, but sometimes you'll hear people call the Euclidean algorithm the lightning bolt algorithm, and we'll actually draw it out so you can see why that is here. So we're going to use two numbers. They're not that complicated here, 210 and 165. So these are relatively small numbers, but they're big enough that you would have to at least think to figure out what their GCD is. You wouldn't be able to just look at them necessarily and know. It's not like if I put 6 and 10 in front of you and you could say, well, their GCD is 2. These numbers are big enough that you would have to think about it. So we're going to use this as an example of how we can use the Euclidean algorithm. Okay, so let's actually do that. 210, 165. Okay, so let's start out. I'm going to use red for the numbers themselves, and I will have to switch colors here a little bit. So I'm going to have, let me zoom in a little bit more. 210 equals some number times, it's going to be easy for us to figure out what this number is here, 165, plus some other number. Okay, so this is our first step of the Euclidean algorithm. Essentially, we're using the division algorithm here. We want to divide 210 by 165, find out what the quotient is, and find out what the remainder is. So, again, I'll let you pause the video. Shouldn't take long. Pause the video, find the quotient and the remainder here. Okay, if we're all back, then we should be able to zoom in here. If we look at this, 210 is equal to some multiple of 165 plus some remainder. Well, the multiple here clearly is 1. 165 is smaller than 210, so you can pull one out, but if you double it, you get, 330, which is bigger than 210, so you can't pull another one out. So that's essentially what you find here for the quotient. You can do this on your calculator. Just take 210 divided by 165. You'll get some decimal. The whole number part of that decimal is your quotient. And then if you subtract this, 210 minus 165, you will get the other number. And so what's that here? 210. We wind up with 45, I believe, here. 45 as our remainder. Okay, so that is what we get here when we use this Euclidean algorithm. Now, let me show you why we call this the lightning bolt algorithm. Let's see, do they have a color that would be good for lightning? How about like an electric blue? How about that? Okay, that sounds good, right? All right, okay. So here, what we do for our next step is we take the b value from the previous step and we put it in the spot. Let me actually see if I can do that a little bit better. We put it in the spot where the a was in the previous step. We do the same thing with the r value. So here, the r value, we put this in the spot that the b was in the previous step. So you'll notice I did these like lightning bolts. That's not actually why they call it the lightning bolt algorithm. They call it because the next step they're going to be shifted down shifted back and down again, so when you draw them, all these lines out, it looks like a lightning bolt. But I kind of made them lightning bolts on their own too. But let's go ahead and set up the next one then. Let's see, red 165 goes here, and black equals times plus. And what we should have here in our next spot is 45. Oops. 45 right here. And that is what we should have to start off the next step. So again, pause the video, figure out what you should get when you divide 165 by 45, and what you wind up with as your remainder. Okay, so we're all back. If we multiply 45 by 3, we get 135. If we add another 45 to it, it would be too big, so we can put that in right here. If I am doing this right, which if I'm not, we'll figure it out pretty quick. So 3 times 45, 3 times 40 is 120, 3 times 5 is 15. We get 135 there. So that should mean what we're left over with here is 165 minus 135, which should be a 30 there. Okay, so that's our second step. Well, now, I want you to pause this right now and fill in the next step entirely on your own. And then when you're done with that, you can come back and we'll do it again together. Okay, we should be back now. Let's go ahead and fill this next step in. I need red first. So remember, our old B value becomes our new A value. So here our old B value was, let's zoom in, 45. And our old R value, which was 30, becomes our new B value. So we got a 30 there. Okay. Now, let's put in the operation symbols real quick. We got an equal to, a times, and a plus. Okay. 30 only goes into 45 once, so that's easy enough. And then what's left over is 15. Okay. Hopefully everybody got that. We've got at least one more step. Remember, we keep doing this until this remainder here, this remainder here, until that equals 0. And we don't have a 0 remainder as yet. Like, all of these remainders so far are not 0. They're numbers. And we keep doing this until we get a 0 remainder. Oh, let me actually put in these lines again. Here we go. So this one goes like that. This one goes like that. And you'll notice if you look at these lines together, you're getting this sort of lightning bolt shape. Like that shape. We don't need those in there. It'll just confuse things, but that's why they call it the lightning bolt algorithm. I'm drawing the lightning bolts in each step because I'm a doofus, but that's why they actually call it that. Okay. So, next up, again, pause the video, do the next step, and see what you get. Okay, if everybody's back, let's go down here to the next step, and what turns out to be the final step. Hang on. So this is 30. This is 15. Let's put in our symbols. We've got a plus, a times, we've got an equal to right there. 30 is, if we can recall this, 2 times 15 plus what's left over? Well, nothing is left over. Oops. Nothing is left over there. And again, I guess I'll put in those lightning bolts here. And over here. But you'll notice at this point, we have finished our algorithm. Here, it took us 4 steps. That is not always the case. It can take you more or fewer steps depending on what the two numbers are to start with. Sometimes it might only take you 2 steps. Other times it might take you like 10, 12, even 30 steps, depending on what these numbers are and how complicated it is to get down to the GCD. But in this case, what we find out at the end here is, let me write this out. Let's do it this way. Then we should get GCD of the two numbers we started with, and the two numbers we started with were, if I remember, 210 and 165. We should find the GCD here is the last non-zero remainder. So here, our final remainder is always going to be 0. The one before that is our GCD, and so in this case, it winds up being 15. So our GCD of 210 and 165 is 15. In other words, 15 goes into 210, 15 goes into 165, 15 divides 210, and (15) divides 165. So we've got 15 goes into both of those, and any other number that divides both of them is smaller. So that's what we find for this GCD here. Okay. Now, that is the actual use of the Euclidean algorithm. But I told you we're also going to be able to use this to find the x and y that we mentioned in our first theorem. And how we do that is we basically start with our next to the last step. Hang on. Are you not going to let me do it here? Okay, there we go. I don't know what happened, but whatever. We start with this next to the last step here. The reason we're starting here is this number, remember, is our GCD. So we're wanting to write the GCD in terms of these original two numbers up here. All right, these two up here. So what we have to do that, let me make this one a little bit better. What we have to do that is start with this step and then backward substitute in up to the first step. So we get everything in terms of 210 and 165. So let me actually show you how that works here. So we're going to start off by writing 15, but instead of having the equation the way we already had it, we're going to find out what 15 equals. So here I have 15, 45 equals 1 times 30 plus 15. So I'm going to rearrange that. 15 equals 45 and then if I rearrange the plus, I should have a subtract. And I'm going to have a times there. And then this should be 1 times, let's move over, 30. So just rearrange that next to last line in your Euclidean algorithm, and you'll have an equation for your GCD equals some numbers. Then what you do is you go up a previous step, so up to this next to last, or the, I guess, second from the last, third from the last step here, and we have our remainder here. We can also rearrange this equation. So let me show you what I mean there. We would rearrange this the exact same way we just did. So this, that still needs to be blue. So this 30 equals some number minus some number times some number. So we just rearrange this equation. We should have 30 equals 165 here. And if we look again, it should be minus 3 times 45. 45, and then a 3. Okay. Now, you might say, so, in fact, let me do all of these just so we have them. You don't have to do things in this order. There are sort of lots of ways you can sort of arrange this by steps. So this last one here was 45. So what I would have here is 45 equals some number minus some number times some other number. And if we rearrange this equation, it should be 210 minus 1 times 165. So 210 minus 1 times 165. So you'll notice I've rewritten all of these in terms of solving them for the remainder. But I said to start with this bottom one right here. This is the one we're starting with. And the reason is this number here, remember, this is our GCD. This is our GCD. So this is what we want to find. We want to, remember this first theorem, we want to write our GCD in terms of the original two numbers. So we've got the GCD written as something. What we've got to do is get it in terms of these original two numbers, 210 and 165. And how we do that, we plug in these earlier numbers here in place of the later ones. So let me do that here. So in other words, I'm going to take this 30 and plug it in for this 30 down here. So let me show you what I mean, and then I'll have you all do the last step on your own. So here, I'm going to leave that 45 alone for now. Hang on, let's zoom in a little bit. Leave the 45 alone for now, and I am going to subtract. I'm going to leave that 1 alone. That's not what I'm changing either. And then this 30 is what matters to me. So let's put parentheses here and parentheses here. Hopefully that's enough room. And what I'm going to do is take this equation I've got up here and put everything there into these parentheses. And I think I might actually need bigger spot, but let's go ahead and do it. So it should be, instead of 30 now, it should be 165 minus 3 times 45. Okay. Let's do this here. So 165 minus 3 times 45. One thing about how I'm doing this on a PDF that makes it a little bit easier is you will notice I can color code these numbers pretty easily. Wouldn't be able to do that on a classroom board so well. So here we get 45 minus 1 times the quantity 165 minus 3 times 45. Now, what we do at this point is we regroup. In other words, I want all of my numbers, all of the numbers in red here, which are what I'm heading for to be the original two numbers. I want all of those to be written in their own terms. So I want something times 45 plus something times 165. So why don't I have you all regroup this so that I have 45 times something plus 165 times something. And go ahead and pause it, work through that, and then we'll come back and do it together. Okay, so let's take a look. If we take this minus 1 here times minus 3, that's going to work out to be plus 3 times 45. So I have 45 plus 3 times 45. Oops. Should give me 4 times sorry, 4 times 45, right? So 4 times 45, so 45 minus 1 times minus 3. If we combine these, they give us plus 3. Right, multiplying negative 1 and negative 3. The minus 1 times 165 doesn't change. I've written this as a plus, so let's put that minus 1 in parentheses. And then over here, I'm going to have 165. You notice we've already gotten a negative number for one of these x and y's here. Unless you have a weird situation, one of these numbers is going to be positive and one will be negative. And don't worry about the question of should we have a weird situation or not. You'll figure it out. And at the end, you should be able to go back and check to make sure your answer works. Okay, so here we've regrouped, we've got a new statement. Now, pause this and figure out for me what we should do next. Like we've done one step here, or maybe 2 steps depending on how you talk about it. But pause this and figure out what should we do next to make this, to get closer to what we want. Remember, we want 15 equals something times 210 plus something times 165. Okay, if we're back, hopefully you all figured out what to do. If not, well, I'm going to tell you. You remember we want 2 numbers down here in our final result. 15 is what we're looking for, right? 15 was this number that we were looking for. We want to write that. And if you recall, the numbers we wanted to write it in terms of are 210 and 165. Right now, we've already got it in terms of 165, but the other thing is 45. So what we have to do is replace it just like we replaced the 30. Remember, we replaced the 30 here. We're going to do the same for the 45 now. We are going to rewrite this as this last statement that we've got here as 4. That 4 is still there, it doesn't change. But instead of 45 now, we are going to go up to our original statement here and rewrite that as 210 minus 1 times 165. Oops. Okay. So this should be 210 minus 1 times 165 and then we have this other part still to deal with. That's already in terms of one of the numbers we need, so let's go ahead and leave it. Let's see. So plus minus 1 times 160, oops. Minus 1 times 165. Sorry, I had to go a row down. Didn't leave myself enough room because I'm a doofus. Alright, so here we go. That means that's where we are. Now we're going to regroup just like we did before. Regroup. And now what we're regrouping is we're regrouping the 210s with the 210s and the 165s with the 165s. So let's do that here. Okay. Now, we only have this one spot where we have 210s, so we don't even need to worry about that. I'm going to get 4 times 210 here still. And now, what I need to do next is combine all the 165s together. So what I have to do here, you'll notice, again, like I did before, is I have to figure out what's happening when I'm multiplying this 4 through this whole parentheses. 4 times the 210 doesn't change anything, but 4 times negative 1 gives us a minus 4. I already have a minus 1 before, so wait, let me zoom in here. This gives us a minus 4. I already also have this minus 1. Minus 4 plus minus 1 equals minus 5. Times times 165. There we go. Okay, so what this should do here is it should give us 15, which is the GCD of 210 and 165. So the GCD of 210 and 165 is now written as a linear combination of 210 and 165. This is a term that you'll have all seen in linear algebra. Let's actually work this out to make sure that we didn't make a mistake. That's the one thing you can do at the end of these, is work them out. So here, 4 times 210, fortunately that one's easy to do. That's 840. And then I'm going to do a minus sign here. And the next one's a little bit harder. It's not that bad, but 5 times 165. Go ahead and pause it and do that. Alright, so 5 times 160 is what here? 5 times 160 is, 800. 5 times 5 is 25. So we should get, what, 825 here. Sorry, I don't really have an access to a calculator, so I have to use my head, which I mean, I guess still works okay, but I'm getting old, so who knows when that's going to go. All right, so here, 840 minus 825, easily enough seen that that is 15 like we wanted it to be. So this method, this Euclidean algorithm that we do, over here, also, if we use the same process backwards, essentially, we can get our GCD written as a linear combination of the two numbers we started with. And that finishes up this first section in Chapter 0, which is on the well-ordering principle, but also a lot of divisibility properties for integers. Talking about GCDs and divisibility and primes and other results. But we also wind up with this result here that we can use this algorithm to find the GCD of two numbers that we start with by repeated use of the division algorithm. The division algorithm. There we go. So repeated uses of the division algorithm let us find our GCD. Once we've done that, we can keep the work we did here and go through that work backwards to find the GCD as a linear combination of the two numbers we started with. And that's pretty much it for this section, I believe. There may be some other stuff that is in this section. If it is, I'll do another video, but I think the next piece spills over into the next section. So anyway, this will be the last video posted on this section, but there are plenty more in Chapter 0, so I'll be continuing to post these. I'll get up as many as I can, as quickly as I can, and hopefully it's enough. If anyone has any questions, feel free to contact me by email or in chat. All right, thank you, and this is our third video. Let me know if you have any questions.